Hello everyone, this is Aidan for Fluid Mechanics 101, and today I'm going to talk to you about the Transition SST model, also known as the Gamma Re-theta turbulence model. So just to start with an overview of what I'm going to talk about today, I'm going to start by going through how the Transition SST turbulence model is different to the K-omega SST turbulence model. I'm then going to look at what are the quantities gamma and Re-theta and what do they represent, and then I'm going to finish off by briefly mentioning the boundary conditions that should be applied to this model. Now, as turbulence models go, this is quite a detailed turbulence model, so rather than go through all of the empirical correlations and relationships, I'm going to focus more on the general overview of the model and understanding what the quantities are, what they mean, and how we should model them. And then you're free to go away in your own time and look at the correlations in a bit more detail if you need to. But hopefully this should be a very useful video to you to understand what the model is and how it works. So just to start off with, what is the model used for? Well, the Transition SST turbulence model is used to model turbulent flows where a significant proportion of the boundary layer is laminar. And this is quite likely to occur and be important for aerodynamics and turbomachinery applications at moderate Reynolds numbers. So Reynolds numbers of the order 10 to the 5. For these flow scenarios, a significant proportion of the boundary layer is likely to be laminar and is likely to affect the overall solution. So the diagram I've got for you there just shows a parallel flow over a flat plate. And just a reminder of what we're talking about here today, over the leading edge of the flat plate and at the start of the boundary layer, the flow boundary layer is initially laminar, and then turbulent fluctuations start to develop in the transition region and they grow, and eventually the boundary layer transitions to becoming fully turbulent. And the length of the laminar and transition regions overall will depend on the Reynolds number, turbulence intensity, and the pressure gradients in the flow. Now, transitional flows and modeling the region of laminar flow near the leading edge is particularly important for aerodynamics and turbomachinery because we're dealing with aerofoils. And if this laminar and transition region occur near the leading edge on the suction surface of the blade, then they're quite likely to affect the strength of the suction peak and therefore the overall lift and drag characteristics of the aerofoil section. So for these flow scenarios, the Transition SST model was specifically developed and is likely to be used for aerodynamics and turbomachinery applications. Now, just a reminder, I'm going to go back and quickly overview the K-omega SST model. And as a reminder to you, the K-omega SST model is typically the model you would use for aerodynamics and turbomachinery applications at high Reynolds numbers. And that's because it gives superior prediction of the wall shear stress. And if you need a more detailed discussion of the K-omega SST model, I'd highly advise you go back and look at my previous video on the topic where I go into this in a lot more detail. But just as a quick overview for today's video, we have the transport equations for the turbulent kinetic energy K and the specific dissipation rate omega, which are there in equations 1 and 2. Now, in the Transition SST turbulence model, we still solve the transport equations for K and omega as we would in the K-omega SST model. And these transport equations are otherwise identical to what they would be in the K-omega SST model, with the exception of the 3 terms which you can see highlighted in red there on the screen. So in the kinetic energy equation, that's the production and dissipation terms, P and D, and in the specific dissipation rate equation, that's the blending function F1, where the blending function controls whether the K-omega SST model is using the specific dissipation rate equation omega or the dissipation rate equation epsilon. And so how are these terms different in the Transition SST model? Well, starting with the production term, the production of turbulent kinetic energy, the production of turbulent kinetic energy is multiplied by a turbulence intermittency called gamma. And in general, gamma is going to take a value between 0 and 1, where really gamma is indicating the state of the flow locally. If gamma is 0, that means the flow is locally laminar and we're near the leading edge of our flat plate or aerofoil. And if gamma takes a value of 1, then the flow is fully turbulent. And physically, gamma represents the percentage of time that turbulent fluctuations are present locally in the boundary layer. So where gamma is 0, the flow is laminar and there are no fluctuations, but when gamma is 1, then the fluctuations are always present and that region of the boundary layer is fully turbulent. So as a pictorial representation of this, if we think of our boundary layer developing over the flat plate or an aerofoil, in the boundary layer gamma will initially be 0, but then once the fluctuations begin in the transition region, gamma is going to be taking a value somewhere between 0 and 1, and then eventually gamma will saturate at a value of 1 where the boundary layer is fully turbulent. And at this point I want to point out and to remind everyone that in the free stream gamma should take a value of 1, and that also includes at the inlet to our computational domain, gamma should be assigned a value of 1 and not a value of 0. And the reason for that is because our free stream is also going to contain turbulent kinetic energy and specific dissipation rate, and we need our free stream to be fully represented by the K omega SST model. And so putting a value of gamma of 1 reduces the transition SST model back to the full K omega SST turbulence model. Now what about the dissipation rate term? Well, the dissipation rate term, dk, is replaced by the form you can see there in equation 4. And you can see there's a min and a max limiter there, and that might appear confusing, and you may have to take a minute to really look at that term and work out what it's doing. But really all that this is doing is saying that when gamma is equal to 1, if you substitute in 1 for where gamma is there, then you can see that dk is going to take its original value, dk, which is what you expect when the flow is fully turbulent. Then the dissipation rate term should be the same as it would be in the K omega SST model. But when gamma takes a value of 0, so in that laminar region at the start of the leading edge, then dk is going to be limited to a value of 10% of its fully turbulent value. And the reason for putting this limiter in is that we expect that even when the boundary layer is laminar and there's no production of turbulent kinetic energy, if there's any turbulent kinetic energy in the flow and the free stream, that will still be damped and dissipated by the wall. And that's why we need to have the limiter in there so that we ensure that the turbulence is still dissipated by the wall. So just a brief summary, and to help you think about what exactly is happening here, then if we consider our computational domain that's full of cells, where the flow is locally laminar, we have the laminar boundary layer, then the turbulent kinetic energy equation we're solving is actually the form given there in equation 5. So we've got the standard transport terms on the left side, we've got the temporal derivative, the convection term, and on the right hand side we've got the diffusion term. But then on the far right there we can see that we still have dissipation, but it's only 10% of our original value, but there's no production of turbulent kinetic energy. Now where gamma takes a value of 1, the boundary layer is fully turbulent, and we reduce to the form there given in equation 6, and we're solving the full K omega SST model as we would expect. But the one term I haven't talked about here is what about the blending function f1? How is that modified and why is it modified? So just a reminder, the blending function f1 controls whether we're locally solving the K epsilon or the K omega model in the K omega SST turbulence model. And if you need more detail, please go back and just have a quick look at my previous video, and that should quickly explain how the blending function fully works. But as a quick overview, the blending function is going to take a value of 1 near the wall and a value of 0 away from the wall, and the blending function is a continuous function that's defined in every cell in the mesh. And so the blending function, if you plot it, might look like something you can see there in the diagram, where f1 is 0 near the wall, and as we move away from the wall it turns to a value of 0. Now in some of the early work and the early papers on the transition SST turbulence model, one thing that was found was that near the wall, in the laminar region of the boundary layer, the blending function f1 would sometimes tend to 0, whereas normally we'd expect the blending function to take a value of 1 and allow the model to take the k omega form of the k omega SST turbulence model. And it was made clear by the authors that we don't want the k omega model switching to the k epsilon model, because we know that the k epsilon model is not as good in the near wall region, particularly if we have a very small value of y plus. And so the blending function f1 in the transition SST model was modified slightly to ensure that the blending function f1 wouldn't accidentally tend to 0 in the laminar region of the boundary layer. And the way it does this is by using a limiter there. You can see in equation 7 where the new term is given by f3, and f3 is just an exponential decay which is governed by this Reynolds number like term you can see in equation 8. And we've got a square root of the turbulent kinetic energy there. So what this is telling you is that in that laminar region the turbulent kinetic energy is going to be very small, and therefore e to the 0 is going to take a value of 1, and that's going to be substituted into the new blending function so that we have a value of 1, and we use the k omega model, which is what we should be using. So that's fine. The correction to the blending function is just a numerical tweak to ensure that we don't accidentally use the k epsilon model. So apart from that, all we've done, remember, is modified the production term and the dissipation term in the regions where the boundary layer is locally laminar. And the way we do that is with the intermittency function gamma. But how do we calculate the intermittency function gamma? The way we do it is by solving an additional transport equation for gamma. So in addition to solving for k and omega, we're now also solving for gamma. And the form of the transport equation for gamma is given there in equation 9. We have the standard convection diffusion form of the temporal derivative and the convection term on the left hand side, and then the diffusion term on the right hand side. And what we've got in addition is we've got a production term and a dissipation term. And what do we expect to happen with these production and dissipation rate terms? Well, where the flow is laminar, in the laminar boundary layer, we expect no production of turbulent fluctuations. There's no production of intermittency, so P will take a value of 0. But then when we reach the transition region, we're going to be producing turbulent fluctuations, and so this P term is going to switch on. And then by the end of the transition region, we expect the value of gamma to have saturated at a value of 1. And there's an additional dissipation term there which you can also see, which if our value of gamma is 1, perhaps in a fully turbulent boundary layer, and we're having a re-laminarizing process, then we expect the value of the dissipation to decrease. So the value of D there allows the boundary layer to re-laminarize under appropriate conditions. But I'm not going to go into that in too much detail here. Really, I'm just going to focus on the production term and how we switch on the production of intermittency in the transition region. And the production of intermittency takes the form you can see there in equation 10. And I've highlighted two terms for you there. There's one term F onset, and there's another term F length. And put quite simply, F onset is going to take the form of some kind of a switching function, where when we're in the laminar region, F onset is going to be 0, and then when we initially move into the transition region of the boundary layer, F onset is going to switch on, and we're going to switch on the production of intermittency. And F length controls the strength of the production. So if F length is very large, that means gamma is going to be produced very rapidly and very locally. So it's going to saturate to a value of 1 very quickly, and this gives a short length of the transition region. So the higher the strength of F length, the quicker gamma saturates to 1, and the shorter the length of our transition region. So both of these terms, F onset and F length, are going to be controlled by additional empirical functions, which I'm not going to go into too much detail here, but you can see what their function is and why they're required in the model. So now we're going to take a small side point to think about how we're going to calculate the F onset term and where the production of intermittency is switched on. And before we do that, we're going to have a think about a different kind of quantity that we might define in a boundary layer. So if we think of boundary layer development from the leading edge of a flat plate or aerofoil, a conventional way we might measure the distance along the boundary layer might be a distance x, and we might divide that by the length of the plate or the length of the aerofoil, for example. That will give us a fractional distance along the length of our geometry. Now, for a CFD code, we can't really use that approach because our geometry could be very general and we may not necessarily have a flat plate or an aerofoil. We may have a more complex geometry. Now, there's an alternative way we can define that distance, and that's in terms of the momentum thickness Reynolds number. That's Re sub theta. And this is a quantity that you might not often come across in CFD, and so I'm going to take a bit of time to explain it to you. Now, the first thing to think about is the momentum thickness and what the momentum thickness is. Now, just a reminder for you from aerodynamics, which you may have come across before, what the momentum thickness is if we have a boundary layer developing over a flat plate or an aerofoil, as you can see there in the diagram, we develop a sheared velocity profile. And for some reason, we may want to replace this sheared velocity profile by an appropriate uniform flow profile. And in order to do this and ensure that the velocity profile and the uniform velocity profile had the same momentum, we would have to displace the surface of that flat plate or aerofoil into the flow. And the distance by which that displacement is moved is given a quantity theta, which is the momentum thickness. Now, that quantity can often be quite difficult to understand, particularly if given the equation which you can see there in equation 11. So an easier way to understand the momentum thickness is to look at the diagram there, which I've got for you on the slide. And if we were to move that surface away by a distance theta and we were to balance the momentum, then what we'd really be doing is balancing the momentum in the red shaded area there and the blue shaded area. And the appropriate distance by which we move the surface theta so that those two momentums balance is the momentum thickness. Now, the next thing to think about is the momentum thickness has a unit of distance. It's a distance that we would displace the surface away, and so we can define a Reynolds number based on that thickness. And because the thickness is going to increase with distance from the leading edge, then the Reynolds number based on the momentum thickness is also going to increase in length as we move along the geometry. So the Reynolds number based momentum thickness is really just a measure of the distance from the leading edge that we are on our plate or aerofoil. And as the Reynolds number is here just a measure of distance, then there will be a Reynolds number at which transition occurs. And this is denoted by Re theta, t, or transition. So at some momentum thickness based Reynolds number from the leading edge, transition will occur. And also at some momentum thickness based Reynolds number from the leading edge, the fluctuations will start to occur. And this quantity is given a unit Re theta sub c, and the c is indicating that this is where the turbulent fluctuations start. And of course this is slightly before where transition occurs. So really these two quantities, Re theta c and Re theta t, are just distances from the leading edge of our geometry. And we're going to use these because we can calculate them in the domain where we want to. So just a small diagram here to help you think about the quantities a bit more detail and help clarify in your mind. If we were to plot the skin friction coefficient along the plate, then initially the skin friction coefficient starts very high at the leading edge, and then as we move along the plate, we're increasing our distance x, but instead we're going to plot that as Re theta, so we're just moving along the plate, and of course the skin friction coefficient decreases as the velocity profile develops. Now at some position along the plate, then the turbulent fluctuations start, but the boundary layer is still laminar and is still transitioning, and so the skin friction coefficient continues to decrease. And then at a certain point, the boundary layer becomes fully turbulent, and This is where transition fully occurs from transition into the turbulent regime, and the skin friction coefficient increases. So you can see there we've got two different momentum thickness based Reynolds numbers at some distance from the leading edge of our aerofoil or plate. And the next thing to think about is that for a standard geometry, a standard aerofoil or plate, we could use experiments or empirical functions to calculate these values. And these are going to be fixed values. Could take a value of 1,000 or 500, say, and Re-theta C is always going to be smaller than Re-theta T. It's very important to remember because the fluctuations always start before the boundary layer transitions. And that's fine for standard geometries, but what about for our CFD code where we have a more general geometry and perhaps we don't know where transition occurs and we'd like to predict it? So the trick that the Transition SST model uses is we introduce a new variable, which is Re-theta T again, but with an overbar. So most papers you'll see it with an overbar. In some cases you'll see with an over tilde or an over line. And this notation is to indicate that this variable is calculated everywhere in the flow. It's a transported variable that we solve a transport equation for. Whereas Re-theta T and Re-theta C were single values, as we saw before in the previous slide. And really they represent the local value, the local distance from the leading edge where either the fluctuations begin or where transition occurs. And what we're going to do in the Transition SST model is solve a transport equation for Re-theta T and then use empirical relationships to calculate the local values of Re-theta C and Re-theta T. And you can see that there in the diagram that we're going to have the overbar Re-theta T calculated everywhere in our domain. And so what is the transport equation for this quantity? Well, as you might expect, it takes a very similar form for transport equations that we use for all properties in our CFD codes. We have a time derivative and a convection term on the left-hand side, and then we have a diffusion term on the right-hand side and a single production term there, P theta T. Now, the way this transport equation functions is slightly different to other transport equations which we might be used to, and so we're going to have a small think about how this transport equation works because it's slightly different. Now, the way you want to think of this transport equation is that we have a free stream value which we specify at the inlet to our CFD domain, and this free stream value we calculate using an empirical correlation. So if we had an aerofoil or a flat plate, we take an empirical correlation for something similar, a similar geometry, and apply that at our inlet. And then what the transport equation allows us to do is to diffuse that value from the free stream towards the wall, where we can calculate the local values where transition and the turbulent fluctuations will begin. And we do this by specifying a zero normal gradient boundary condition on the wall. Now, this is conceptually different to the way we use transport equations for turbulence and the way we use them for velocity and temperature, where, for example, for the temperature equation, we might have a fixed temperature on the surface, and the temperature and the heat diffuses from the surface into the flow. So the diffusion is really from the surface and from the wall into the flow, and you can really see this in the development of a thermal or momentum boundary layer. We have a uniform free stream, and then the momentum that's taken out of the flow by that wall diffuses into the flow. And this is opposite to what we have in this transport equation, where the free stream value of Re-theta T diffuses in towards the surface, and that's the way you want to think about it. And I've got a small diagram for you there to help you remember that Re-theta T is calculated using an empirical correlation in the free stream, and then we diffuse that value in towards the surface. That's the way you want to think of it. And the way we control this is with the production term P theta T there. So how does this work? Well, the way we do it is we use the production term to force the value of Re-theta T to take the empirical term everywhere in the flow except for in the boundary layer. And this also may take a bit of thinking and a bit of getting used to first. But if we take a look at the form of the production term there in equation 13, what we see is that there's a blending function f of theta, which is similar to the blending function in the k omega SST model, and it takes a value of 0 in the free stream and 1 near the wall. So when we're near the wall, the blending function is 1 and the production term is turned off. And what that means is we're near the wall and the free stream value can convect and diffuse in from the free stream to the wall. However, when we're in the free stream, the blending function takes a value of 0, and that second bracket there is going to force the value of Re-theta with the overline to take the value of the experimental term there, Re-theta t. So anywhere where there's a difference, perhaps due to a geometry or some convection or mixing, this production term is going to force the transported value with the overline to tend towards the value of the experiment that we apply at the inlet. So in effect, what we're going to get with our field is a constant value everywhere in our domain equal to Re-theta t, but then in the boundary layer where we're interested, this production term is turned off and we're going to get a diffusion towards the surface. So just a final little bit to help you conceptualize the model and think about what's going to be going on. What we'll end up with is a value of Re-theta t with the overline calculated in every cell in our solution domain. And this is of course a local model because we're going to have a value in every cell, whereas the empirical and the experimental models we saw before, we only calculated a single value on the wall. And once we have a value of Re-theta t in all of the cells, we can use that to calculate values of f length and f onset in each of those cells in the domain using some empirical and algebraic relationships. And if these values are beyond a certain threshold, so if f onset is turned on and f length is turned on, then we're going to have a production of intermittency in each of those cells. So it's very important now to think of it on a cell level, that in an individual cell we're going to turn on a production of gamma, which is going to result in us producing intermittency, which is going to allow the boundary layer locally to transition from a laminar boundary layer through transitional and into the turbulent boundary layer there. So it's quite a clever model, and it may take a bit of time for you to sit down and think about getting used to. It definitely took me a little while to try and work out exactly what was going on. And the one remaining thing is that to close these models and to complete them, there are several empirical correlations that we need to close the models. And if you look in the various papers and in the user manuals, you may find some of these models. And one such example is the free stream value of Re-theta t, which you apply at the inlet to your domain, for example. And this free stream value is going to be a function in general of the turbulence intensity and the pressure gradient. So with aerofoils and flows with a pressure gradient in the streamwise direction, that's always also going to affect the momentum thickness Reynolds number at which transition occurs. And I've put for you there just an example plot to help you think about exactly what's happening. The turbulence intensity I, as we increase the turbulence intensity, we expect the length of that transition region and the laminar region to reduce, and as a result that's reflected in Re-theta t reducing. So remember, Re-theta t is just a measure of the distance from the leading edge up to the point where transition occurs, and we can see in the graph that as the turbulence intensity increases, that distance reduces. And there are several of these correlations and bits of it experimental data which you can find in the papers and in the user manuals, and I'll link those in the description to this video as well, so you can have a look if you want to see in a bit more detail. But one thing you may come across as you're looking at these is some of the correlations, like the ANSYS Fluent correlation and the early correlations by Mentor et al. Are proprietary, and so you can't actually find them. But a lot of the later correlations you can look at and implement and check in your own CFD code if you want to. So just a closing summary of what I've talked about today, and to really wrap everything up, a reminder that the Transition SST model is actually a 4-equation model. So even though it's called the gamma Re-theta model, there are actually 4 variables we're solving for there, because we're still solving for the K and omega equations in the original K omega SST model. And so we solve those 2 additional transport equations, and remember that the only modifications to the K omega SST model are the production term, the dissipation rate term, and the blending function there. And A small point here on mesh resolution, you'll see this in some of the user manuals, that it's highly recommended that the mesh has a Y+ value of less than 1, particularly important for aerofoils and turbo machinery, and the reason for that is that Y+ actually seems to have an effect on the predicted location of transition as well, so it will have a significant effect on the results if your mesh is not sufficiently resolved. And it may also be useful to you to just have a check and have a look at what correlations and what free stream values are you actually applying for Re-theta and for gamma, remembering that gamma should be assigned a value of 1 at the inlets and the free stream, not a value of 0. And then when you're post-processing your solution from the Transition SST model, gamma is going to be the quantity that indicates the local behavior of the boundary layer. So where gamma is equal to 0, you've got a laminar boundary layer. Where gamma is between 0 and 1, the boundary layer is transitional. This region is likely to be quite short. And then regions where gamma is equal to 1, your boundary layer is fully turbulent. So gamma is quite a useful quantity for you to plot and post-process when you're looking at your solutions. And as always, I'd just like to finish this talk by thanking all of you for continuing to support the channel. I really do appreciate it. And I'd like to thank in particular my patrons for supporting the channel. I really do appreciate their support and all of your support as well. And if you've really enjoyed this video, if you found it useful, or perhaps there are things that you really liked or things that you'd like a bit more explanation on, please just drop a comment in the comment section below. I do try and get to all of the comments as quickly as I can, and I do really like hearing from you. I'd like to hear what things did you like and perhaps what things you'd like to see more of in my videos. And if you did really enjoy the videos and you'd like to give something back and say thanks for things that you might have learned in this video, there are a number of ways you can do this. You can either follow me on Patreon, make a donation through PayPal, or even just buy me a coffee if you just want to say a quick thanks. And links to all of those are in the description below this video, as always. And I'd just also like to mention as well that for those of you who do follow me on Patreon, you do get some additional benefits. I upload all of the lecture slides that I do for all of these lectures on YouTube to Patreon, so you can get access to those as soon as they're up if you want to study them in your own time, perhaps, and print the lecture notes off for yourself. And you also get access to my Fundamentals in CFD course as well, specifically on Patreon. Once again, thank you guys all very much for watching, and I look forward to hearing from you in the future.